Okay, so good afternoon. So the second lecture will be a continuation of the first one, as I didn't finish what I like to do. And then I'll go on with two photon exchange in lepton-nucleon scattering. So just to remind us what we did yesterday, I explained you in some detail the present status of the proton radius puzzle. So we have seen the measurements of electron scattering, which are in agreement with the proton radius as determined from the electronic hydrogen atom, which give a radius which is markedly larger than the extractions from the muonic hydrogen, which is a system where the muon is much closer to the proton, and hence one has a much enhanced sensitivity to this proton radius. That's why one accesses a radius here with a precision which is typically 10 times better than in electron scattering. Now, it's not only more precise, it's also different. So the proton radius is smaller, and this is a big effect. So it's 8 sigma, and I already was going in quite some detail to the possible corrections and how we understand them. And we have seen that hadronic corrections, to the best of our knowledge, can explain about 10% of this effect only. So with relatively good precision. So now I think I will have a problem with fonts. I don't know when it started up. We have seen this yesterday. So here there was the Lamp-shift formula, and so this is just meant to explain that the difference of the 310 microelectron volt is the difference between the two radii. So we went through these possible explanations, and so if none of those works, then I mean, people see this as a possibility to extract new physics. So now let me go on with where I left last time, and so the next stages in this puzzle. So there is an ongoing program, quite active. And the next stage on the experimental side for the muonic hydrogen Lamp-shift is to do measurements on equivalent systems where you replace the target. So instead of having a hydrogen, you replace it by a deuteron or helium-3 and helium-4. So each time with a muon. And so one would like to see if one has a similar situation happening when you have different targets. The second new development, which I also comment in a bit of detail, is that there are new measurements which have been done actually, which are being analyzed, where one is doing more precise measurements, so higher precision measurements of the ordinary hydrogen Lamp-shift, so the historic Lamp-shift experiment, so to say, with higher precision, because these experiments they are in agreement with electron scattering, but with relatively large error bars. So one would like to see if this agreement is real, or if it's just because one doesn't see it because of the error. Now, also on the electron scattering side, there is quite some development. So one of the sticky issues is how to extract radii from form factors. I mean, typically these form factor measurements go down to about 10 to the minus 3 GeV squared, and although this is a small number, it's not exactly, of course, the slope at the origin, and one needs to do some extrapolation, and so there's some new developments going on. Ultimately, so new experiments at lower Q squared will eliminate this extraction procedure, and also radiative corrections and two photon exchange corrections, so I will come in some details in the second lecture to these effects. And then, so as I was mentioning already, just new electron scattering experiments where these form factors will be measured down to about 10 to the minus 4 GeV squared are also underway. And lastly, if there is something special with the muon system, so with the muonic spectroscopy, and if some new particles would couple, for instance, to muons, you would also see that when you do scattering of muons from protons. So we would like to compare also with the same kind of precision muon scattering versus electron scattering to understand this puzzle. Now, I would like to go in a little bit of detail to these individual points, just to give you a flavor of the current state of this research. So on the experimental side here, the people who are doing the muonic atom experiments have done also experiment on the muonic deuterium, and this is kind of the status plot here, what is extracted. So what is shown on this plot is a similar measurement, so having a deuteron and then capturing a muon in this system, so forming a muonic deuterium, and measuring this charge radius. Now this is a busy plot, so I will just guide you through this. So what is shown on this plot firstly is the measurement of electron-deuteron scattering, so this is the ordinary scattering experiment. So this is just an expanded plot, so the error doesn't look very good here, but this is still like it's about a 2% error, I think. And this experiment is being redone also to have this error bar. So that's the current status of the elastic electron-deuteron scattering. And if one compares the radius with the muonic case, there are two observations. So the first one is there is one independent piece of evidence, which is the so-called hydrogen-deuterium isotope shift. So isotope shift, this is a difference between a 1s and a 2s level in the ordinary hydrogen, and this allows to get a measurement, very precise measurement of the difference of the RMS radii squared of the deuteron and the proton. And so this gives here a specific number. And now, of course, to get the deuteron out, you need to know the proton. Now, depending which value you put in for the proton, you get, of course, two different values. So if you plug in the value from ionic hydrogen with this number for the isotope shift, you get this number. If you plug in the electron scattering value, you get a bigger error and you're sitting here. So this difference is nothing else than the input from the proton radius. Now you would like to compare this with the direct measurement of the muonic deuterium, and this is actually shown by these red points. So now you will ask, so why are there 4 points here? So as I showed you before, in the case of the proton, to get the radius out, so we have seen that the leading hadronic corrections are the 2 photon corrections. And these 2 photon corrections depend on polarizabilities. So we have seen that in the case of the nucleon, the polarizability, which is typically proportional to the volume of the system, is only, for nuclear system, nucleon, it's only 1,000 of this volume. So this is why, so a proton is a very stiff object, and these polarizabilities are relatively small effects. In the case of the deuteron, which is a loosely bound system, it's basically understood to first approximation as pion exchange. So basically the polarizability is proportional to the volume, so it's a very polarizable system. And so these effects are much larger, and depending on which correction you apply, so these are here different corrections, one gets quite some dependence. Now, so there is a model dependence, so right now this is still preliminary, so it's not yet published, although these data have been released already 2 years, precisely because in this case, one would like to understand better the model dependence coming from this effect. And I would like to just show you what is the main dependence here. So very similar to the analysis which I've shown you yesterday, one can calculate the correction to this Lamb shift from elastic, which means so 2 photon exchange with the nucleon in the intermediate state, and then inelastic, different inelastic intermediate states. And I will not go to all of them here, but the leading uncertainty, so one can see here from this number, it's by far the largest number, is just coming from the breakup of the deuteron, basically, into a proton and a neutron. So one is basically hitting some nucleon within the deuteron, and this has such a large uncertainty because the average value of Q squared in this 2 photon box and the energy of the photon in this 2 photon box is a very small number, typically like 3 to 6, 10 to the minus 3 GeV squared, and there are practically no data in this region, so no high accuracy data. So there are new experiments actually going on to improve this situation, but this is the main origin. So the aim is here with the new experiments to bring this number down by a factor 4, basically, and then one would know this correction here, this two-photon correction, much better. So the summary for the deuteron at this point is a little bit indecisive, in contrast to the proton, where one can do very accurate calculations, where the polarizability effect is only like 10%. Here, this effect is much larger. So nevertheless, so if we, despite this larger effect, if we take this model dependence into account, this still seems to align with the muonic hydrogen radius and not with the electronic hydrogen radius. So there is so one seems to confirm this puzzle also in the deuteron system, but with a larger error at present. Now, very recently actually, so in June of this year, there was a workshop where most people working in this field have been present in Mainz, and for the first time there have been results shown on the helium-4. So helium-4 is a very compact nucleus in contrast to the deuteron, so also quite well understood, and the polarizability effect is much smaller. Now, so that's why the theory can be done more accurately here for these quantities. And so if one compares, in this case, the radius here from electron scattering, 1.68 Fermi with 1.677 Fermi, they're in perfect agreement. So this is very puzzling. So it was actually very puzzling when this was presented. So there seems to be a perfect agreement, and also here the theory, actually there's a state-of-the-art calculation based on chiral effective field theory with the most modern nucleon-nucleon potentials, which was reported is relatively well under control. So there is not so much to doubt here. And so one sees that there is a perfect agreement. So now coming back to this possibility of new physical explanations, so if there is new particles coupling to the muon, in first approximation, it shouldn't depend on which quark this particle is coupling to in the target. So if it's coupling in a proton or in a deuteron or helium, so only the nuclear wave function should enter, but the effect should still be there. So if we don't see this effect in some targets, so it points that the effect is maybe there only in the case of nucleons or deuterons. So, and also, this was actually even more recently. There was a Gordon conference just about a week ago, and they showed for the first time also the line in helium-3. And also in helium-3, although they didn't show a radius yet, so it's too early, but the preliminary analysis also confirms that for helium-3, one sees no effect. So it's right now it's a bit of a puzzling situation. So one sees the effect in the muonic spectroscopy for the proton, for the deuteron with larger model uncertainty. One doesn't see it in helium-3, helium-4. So
go back to the case with neutron. It's the discrepancy between the pro-data and the
yes.
mu h. Isn't the difference is due to the proton charge rating?
Yes. So, okay, what is done here to get because what is shown is the deuteron charge radius. Now the deuteron charge radius, so if you don't look at the red results, everything here is from electron scattering first. Yeah? So for the isotope shifts, this is the ordinary hydrogen, 1s, 2s. So it's a very precise number. And so this is the electron-deuteron just scattering. And now to get from this isotope shift, the deuteron radius, you need to stick in the proton radius. So you can do this in two different ways. So either you plug in the electron scattering value, and then you get this number, or basically it's called co-data because it's a combination of electron scattering with electronic hydrogen. So you get this number. If you stick in the muonic hydrogen value for the proton, you get that number. So it has much smaller error. So this difference is just the reflection of the puzzle on the proton. So it has nothing to see with the deuteron. Okay? And then you would like to see if you do the direct measurement on the deuteron, so when you have muonic deuterium, either this point ideally should line up here or should line up here. So lines up here, it means it's in agreement with the value of the muonic hydrogen and not with the normal hydrogen. So it seems to line up within the model uncertainty, I would say. So, but yeah, one would like, of course, to improve this model dependence in the case of the deuteron. Now, let's see how one can make sense of this, because it's an 8 sigma effect, so we should really understand this. So let's go back to the cases where you have electron systems, so either the electronic hydrogen spectroscopy or the electron scattering. So let's start with electronic hydrogen spectroscopy. So the value which is extracted usually, so this is here shown by this blue band. This is a combination of 15 measurements. So, and you see all of them, they scatter around this band, and each measurement individually is not of such great precision, but the combination of the 15 is determining this codata band. And just for your comparison, this pink band here is the very precise measurement from the muonic hydrogen. So this difference here is this discrepancy. Now, from these 15 lines, only these lines here in pink on the top are direct lamp shift measurements, 2s1/2, 2p1/2. All the other lines are transitions between different principal quantum number levels, where you also have sensitivity, of course, to the wave function of the proton. It's just that in this case, the Rydberg constant is entering, you are doing transitions between different n levels, whereas here one has transitions within the same n=2 level. So you see, if you just look at the lamp shift by itself, you wouldn't get such an accurate measurement. So people have argued maybe one can shift all these measurements by adjusting the Rydberg constant. You need to shift it by about 4 to 5 sigma though. And so if the lamp shift is not affected by this, but maybe within these error bars, this difference is not really significant. So that's why one would like to have more accurate measurements for the lamp shift in the ordinary hydrogen, and that's actually something which became possible very recently. And just to show you the historical perspective here, so the lamp shift was measured early on, so end of the 40s, and the most accurate present-day measurement actually dates back already to 1980. So here from Landin and Pipkin, who obtained this number, and so this determines the proton size only to an accuracy of about 3%, which is not so great because the electron scattering already gives it to 0.5%, and the muonic hydrogen gives it to 0.5/mil. So one would like to improve this number, because at present this is still only the most precise measurement here from the lamp shift. Now these experiments are quite tough on the ordinary hydrogen, more complicated actually than the muonic ones. And so such experiments are only being done apparently once every 33 years, because this experiment came 33 years after the pioneering experiment. And it's just a coincidence, if you count 30 years further, it's 2011 or 13. And the experiment was being done last year. So it's the 33-year cycle. So if they don't get it right this time, then I must wait for another time. So this is it's being done by a group around Eric Hessels at York University in Canada. And so this is the same plot, just shown differently here. And these are the 3 lamp shift lines, and the others are the different transitions between different n levels. So that's the muonic hydrogen result, and that's the average of all these lines. And the new experiment is shown arbitrarily, because the analysis is still ongoing, but it shows the precision which will be achieved. So it will improve significantly. And now the question is, if this stays right on this band, so with this kind of precision, then this effect means you cannot explain it by changing the Rydberg constant, because it doesn't enter here. So it means there is a real problem. If these points are moving towards here, then basically the problem is shifted to the electron scattering. So one has to see. So I think this is one of the most important pieces of information at this point of view, at this point in time, which can shed a further light on this. So hopefully, so the people who analyze this, they are saying that within 6 months these results should come out. So I think we will see. So let me just make a summary here of the first part. So this is on this proton radius puzzle. So we have seen that so the precision muonic atom spectroscopy has really changed our textbook knowledge of the quantity as a proton radius, which was thought to be well understood. And so it generated the large activity, basically large activity on the theory side to scrutinize the corrections. And from the QED side, I've shown you there's absolutely no doubt. From the hadronic physics side, so these polarizability corrections have been estimated by several groups in different approaches. Typically, they're of the order 10% of the needed effect, and they can be accurate. They can be calculated quite accurately because one can relate them to structure functions. So that's why, which are measurable. So that's why it's very unlikely that one can explain the full effect just by hadronic physics. Nevertheless, so because we didn't explain the effect, so maybe one is really overlooking something. And as I just showed you, so this actually already made this slide already a few months ago. So actually results on ionic helium-4 already shown, and helium-3 have been shown very recently. So this is already something which is there. The electronic hydrogen lamp shift result will be there in half a year from now, so we'll give a new element in this puzzle. And so what I'd like to discuss in this lecture are new electron scattering results, which are also planned in the next 1 to 2 years, and muon scattering results, which are planned in the next 3 years or so. So hopefully this puzzle will be more interesting than the one which is shown here on the left. So because that will be a hard one to continue. Now, so yeah, I think I will have a problem here with the fonts. I saw this just in the PDF version. Is that yes? Okay, so new scattering experiments, electron scattering and muon scattering experiments down to very low Q-squared. So the idea here is to remove the uncertainty from the extrapolation. So by going down to Q-squared values, which are typically in the range 10 to the minus 4 GeV squared, and so both at Jefferson Lab and in Mainz, there's several experiments either being done already or just coming up this year. So this will be actually one of the first experiments in the upgraded Jefferson Lab, which will be running because it doesn't require actually the high energy beam. So it's a low energy experiment, so which will be done. And then, so in the 2 or 3 year time frame, there will be also a new experiment at PSI, which is called MUSE experiment, which is a muon proton scattering experiment at low Q-squared. And the idea is to test this lepton universality. So if there is something special in the muonic system, one should see it both in the spectroscopy and in the scattering. So this will measure electron and positron scattering combined with mu plus and mu minus scattering on a proton. So it will measure both the different charges here and the different lepton flavors. So and this is in the q-squared range, which is between 10 to the minus 3 and a few 10 to the minus 2 GeV squared. So it's basically a test also of two photon exchange corrections, because by changing the sign of the lepton, one can access these two photon corrections directly. Now, let me go in this lecture in some details of these analysis of electron scattering experiments and our understanding of this. And I apologize, so I see that this is also not coming out here. I think I will just restart this, because that's probably the only way. Are there any questions in the meantime? So on the first lecture, so yes?
You just mentioned the new experiment for the EP would go to the 2 times 10 minus 4 GeV squared.
Yes.
But the issue here is when you do the very low Q square, for example, the previous one is go to 0.002. So now you will go to even lower, 10 times lower. But in order to get this do the extrapolation, surely you have to take care about the two photon exchange part.
Yes.
But the difficult thing is you have fit the main important part of the pronounced part of the two photon exchange is the high Q square. So you have pick up a certain parameterization, go to the low one, and even, but the situation here is if you go to the low Q square, even the two photon contribution is supposed very small, but it might still have the contribution to the. So the global fitting I found is rather difficult. For example, in the previous the PhD thesis, he used probably 10 times different presentation. And actually, no one is good for the global fit. Some is good for the low, and some is good in the medium.
Okay, there are two things. So from the theoretical point of view, I mean, the q-squared range, which is accessible already now, is like 10 to the minus 3, which is smaller than n pi squared, actually.
Yeah.
So which means that unless there is some new particle, but if there is not, I mean, one can use chiral perturbation theory. You are at q-squared value smaller than n pi squared. So one is within the radius of convergence already of chiral perturbation theory, definitely. So one could, and this has been done actually already. And so this is in agreement with the extraction, the pure experimental extraction, which you referred to. So of course now when you go to the pure experimental extraction, then you may indeed ask the question, so do you want to include all the data? Up to which q-square do you need to include the data? Because the uncertainty from parameterizations of two photon exchange or other effects at larger q-squared should not matter at the lower q-squared. And so there is a trade-off. So in the sense that just doing a linear fitting at very low q-squared is something you will lose the accuracy, because you will restrict yourself to a very small set of data, and then you will not achieve the kind of precision which is needed. So, because there is no point to increase the error bar, and then it will of course agree. So you need to include some data at larger q-squared in order to, just from the point of view of increased statistics. So, but then, so the proposal there would be to use then for this extrapolation like effective field theory, because one is really in a range where you can apply it. But this is a point which is being debated indeed. It's